And really, we can simplify it even further. This is just motion on a line. Okay, so we're going to be talking about a particle moving back and forth on a line. We'll be using a physics concept that we already have discussed multiple times, which is the relationship between position, velocity, and acceleration, right? And so it's important to remember that. It's been a while since we've discussed it. But usually when we talk about a position function, we'll reference it as s of t. I don't know why s, but it's just the way it is, right? And then velocity is the derivative of that. And then acceleration is the derivative of velocity, or the second derivative of position, right? So those are important in today's example. All right, so remember that a derivative of position is instantaneous velocity, whereas average velocity would be just our Algebra 1 definition of slope between 2 points of a position function. And then instantaneous rate of change of velocity with respect to time is acceleration. And there's actually another one. Well, there are actually multiple more. There is a derivative of acceleration. That's called the jerk. And so the jerk is an instantaneous change in acceleration. And it's called the jerk because that's what it feels like. You might recognize this feeling from like when you see me on the light rail trying to hang my bike up and the light rail starts and I immediately fall over. That's the jerk. That's the change in acceleration. Also, just the worst. How did that idea get greenlit? Like, let's have people lift their bikes off the ground on a moving train and try and hang them up from the ceiling. Just what a poor design. I hope none of your parents were like involved in designing that, and I'm not insulting anybody here, but just from experience, I've fallen over onto people from trying to hang up my bike. All right, so that would be the third derivative of position. I think we do talk about that a little bit in our example. But then after that, like the change, instantaneous rate of change in jerk is, and this is real, it's going to sound like I'm making this up, that's called snap. The instantaneous rate of change in snap is called crackle, and the instantaneous rate of change in crackle is called pop. So snap, crackle. Are you guys even familiar with what snap, crackle, pop is? Like as a, you are? As a, I guess, ad campaign for Rice Krispies? All right. So here's the example we're going to do. We're given this position of a particle, position function. We're basically going to dissect the motion of this particle over a given time period, okay? And so here's what this particle is doing. It's just moving on a line right to left. So the first thing we're going to do is find its velocity. So all I have to do to find its velocity at time t is take the derivative of its position function, right? Which this is just a polynomial, so the derivative is pretty straightforward. We're just going to get 3t squared minus 12t plus 9. Great. Done with A. What is the velocity after 2 seconds? Well, for that we just want v of 2. Oops, not v of t, v of 2. Which is 3 times 2 squared minus 12 times 2 plus 9. So that's 12 minus 24 plus 9. So negative 12 plus 9, so negative 3. And the units would be meters per second. So I said this is just a particle moving along a line. All right, so here's the line. Here's the particle. All this is telling us is that the particle would be moving at time 2 seconds. It's going to be moving to the left because it's negative 3 meters per second, right? After 4 seconds, three times 4 squared minus 12 times 4 plus 9. All right, so what do we got there? What's 16 times 3 is 48 minus 48 plus 9. So this is 9 meters per second. All right, so that just says that after 4 seconds, the particle is then moving to the right. So this is at 2 seconds, and then at 4 seconds, it's going that direction. It's positive. Okay? So the particle isn't just traveling in one direction. It's doing multiple things, right? So it's time, let's see, time 2 seconds moving to the left, and then at 4 seconds, it's already turned around and it's moving back to the right. All right, well, when is it at rest? The particle will be at rest when its velocity is equal to 0, right? So what we want to do is take the velocity function, v of t, and set it equal to 0 and solve for that time. All right, so that's 3t squared minus 12t plus 9 equals 0. All right, well, I can divide a 3 out from everything, and that's going to give me t squared minus 4t plus 3 equals 0. And this actually, I think, factors. T minus 3 times t minus 1 equals 0. All right, so that's going to give me two values of time, right? So t equals 1 second and 3 seconds. The velocity is 0, so the particle is at rest. And that could mean it stopped. There's two ways the particle can come to rest, right? So it has to come to rest to be able to turn around and change direction. Or it could just be coming to rest and then continuing in the same direction. So, right, even when you throw something up in the air, so if I throw this pencil up in the air, there is a point at which its velocity is 0 at the apex, at the top, right? Momentarily. So for any particle to change direction, it will have to come to rest. So when is it moving forward, aka in the positive direction? All right, well, we found the only two times that the particle is at rest is time 1 and 3. That means at all other times, it's either moving forward or backward. So if we're thinking about it moving on a horizontal line, it's either moving to the right or to the left at all other times. So the way we can figure this out is, let's plot a number line. I'm going to put the two times it's at rest on that number line. So at time 1 and time 3, I'm going to make a note above that number line that what I'm looking at is specifically the velocity function. Because velocity is what's going to tell us direction, right? All right, and then we're just going to choose a value. We know that at these times, the velocity is 0. So we're just going to choose a value from every other section of the number line to plug into the velocity to see whether it's positive or negative. So give me a value from this section of the number line. You can throw it in the chat. Sure, 0. If I plug in 0 to the velocity, do I get back a positive velocity or a negative velocity? If I look at v of 0, I get 9, which is positive, right? And that's all I care about, if it's positive or negative. That means on that entire time frame, so ostensibly time 0 to time 1, the particle has to be traveling in that positive direction, right? And I know that because I know the only times the velocity is 0 is at time 1 and time 3. So to be able to turn around, the particle has to come to a rest. Just like for the pencil to come down, its velocity has to be 0 at its apex, right? So the velocity, the particle can only be traveling in one direction on any other part of this number line. So here it's traveling in the positive direction. All right, choose a value on this section of the number line. Between 1 and 3, so many choices. Okay, 2. Yeah, I agree. Let's choose 2. If I plug in 2, v of 2, is that positive or negative? Well, we already did this. It's negative 3, so it's less than 0. So that means from time 1 to time 3, the particle is traveling in the negative direction, or left, if we're thinking of it on a horizontal line. And then choose a number on this section of the number line. Probably makes sense to use 4, I agree, especially since we already found that the velocity at time 4 was 9 seconds. So v of 4 is greater than 0. So the velocity is positive on that time interval. So the question asks, when is it moving in the positive direction? There are 2 time intervals where it's moving in the positive direction, so our answer would be times 0 to 1 and time 3 to infinity. In this case, since we're talking about time, probably doesn't make sense that we would use negative values, which is why I'm starting at 0. All right. So we're going to continue analyzing. We're going to skip E because it's dumb and I don't like it. And I'm the boss. So I get to decide. But it's just I'll show you what the diagram looks like. You don't have to do this for the AP exam, so I just tend to skip this question. Particle motion diagrams you probably have seen in Steinert's class. All right, find the total distance traveled by the particle during the first 5 seconds. So remember, I can't just go s of 5. That doesn't give me distance, that gives me position. So all that tells me is where the particle is with respect to where it started, right? So let me give you an example of what I'm talking about here. If I'm the particle, and let's say from here to my wall is 5 feet. If I do this, touch my wall, you can't see me, I'm off camera, but I touched my wall, and I come back to where I started, right? And I said that was a distance of 5 feet. The total distance I traveled would be 10 feet, because I went there and back, right? But my position at the time that I finished is 0, because I finished where I started. So there's a difference between position and distance, right? So the way I need to break this down is in trips. And I need to find trips that it's traveling in one direction. And I can do that by using my little velocity diagram. I've already broken down when it changes direction, right? The particle changes direction at 1 second and at 3 seconds. So I'm basically going to break it down into 3 trips. I'll look at the distance it went from time 0 to time 1, the distance it went from time 1 to time 3, And then the distance it went from time 3 to time 5, which is what they're asking for the first 5 seconds, right? All right, so to get that first distance from time 0 to time 1, I can just subtract the particle's positions and take the absolute value. So its position at time 1 minus its position at time 0. And that'll give me the distance it went over that first 1 second when it was traveling to the right. And I'll do plus the position at time 3 minus the position at time 1. Take the absolute value of that. And then finally plus the position at time 5 minus the position at time 3. And that'll give me the distance it traveled over its last trip. So I'm breaking it down into the 3 trips it takes based on direction. So this distance plus this distance plus this distance, right? And I am using my original position function. So that's the t cubed minus 6t squared plus 9t. So I'll give you an easy way to do a problem like this. If I'm asking for this on an exam, you can just show work like I did here just by using the name of the function. I don't need to see that you can hand plug in values to a polynomial and evaluate that. You all passed Algebra 1. I trust that you're able to do that. But this is where you can kind of use your calculator to make things a little bit easier for you. So this is how I would do this. Let's go here and enter our position function. So that's the t cubed minus 6t squared. So it's going to be x cubed minus 6x squared plus 9x. All right, then we can go to the main screen. I'll quit just out here. And there's a shortcut to get to y1. I think I mentioned it before, but if you do alpha trace, that'll pull up a shortcut to your y variables. And I'm going to choose y1, and you can use function notation. So I'm just going to put exactly what I wrote, which was s1 minus s of 1 minus s of 0, but I'm going to do y of 1 minus alpha trace y of 0. Boom. That's 4. So that's the distance it traveled over that first 1 second. So 4, I'll write that down, plus, here's another little trick. If you do second enter, it'll pull up what your last input command was, and then you can just edit over these. So then I want y of 3 minus y of 1. Now this one, remember, it's traveling to the left. So I'm going to expect that this comes out negative, but we're taking the absolute value because we're just talking distance here. So over that second 2 seconds, it traveled another 4 meters, and I'm gonna call that positive 4 because I'm taking the absolute value, plus, and then we'll just edit. I'll do 5 and 3. So over that last 2 seconds, it must have sped up quite a bit because it covered 20 meters. All right, so now I'm looking for total distance, so I'm just adding those together, right? 4 plus 4 plus 20. So 28, my units are meters. All right, so G, find the acceleration at time t and after 4 seconds. So first, let's just find the general acceleration. A of t, that'll be the derivative of my velocity. or the second derivative of my position, let's look at my velocity was here, 3t squared minus 12t plus 9. So the derivative of that is going to be what? 6t minus 12. The acceleration after 4 seconds would then just be 6 times 4 minus 12, which is 24 minus 12, which is 12, and my units would be meters per second squared. All right, graph the position, velocity, and acceleration functions from 0 to 5. I'm just going to do this in Desmos, and I'll just point out some of the important characteristics. All right, so my position function was all right, so there's position. Let's get a zoom. There we go. So it's this cubic function. So velocity is the derivative of that. Oh, yo, are you serious? Come on, Desmos. Will it not just take the derivative for me? All right. Which was 3t squared oh, sorry, that should be 9t. 3t squared minus 12t plus 9. Oh, it doesn't like that? Okay. Okay. All right, so that's the velocity. So you can see when we have the zero slope on the blue graph, we have a y-intercept on the velocity graph, right? And we have acceleration, a of t is 6t minus 12. Great. And again, we have a zero slope on my parabola right here at the vertex, and I have my y-intercept of my linear graph right there in the same x location. Now, the last thing they want us to do is compare when is the particle speeding up versus slowing down. And remember, what we want to do to figure that out is compare acceleration to velocity. So the particle will speed up when the sign of acceleration and velocity agree, and it'll slow down when they disagree. I always like to think of the throwing something up in the air example, right? So if I throw a pencil up in the air, when it's going upwards, it's slowing down. That's because the acceleration, which is due to gravity, right, is negative 9.8 meters per second squared. But the velocity is positive. It's traveling upwards, so the velocity is positive, but the acceleration is negative. They're fighting against each other, which causes the particle to slow down. But when it's coming back down, it's speeding up because the velocity is negative and the acceleration is negative. They agree, so it speeds up. So what we want to do is take a look at acceleration versus velocity. To do that, I want to make a similar number line plot for acceleration like I did for velocity here. So I'm going to set the acceleration equal to 0 and solve. So that means 6t minus 12 is equal to 0. Solve for t, add the 12, divide by the 6, we get t equals 2. So if I look at my acceleration graph at time 2, and I'll note that I'm using acceleration here, my acceleration is 0. So at all other times, the acceleration has to be either positive or negative. So we're just going to test. That breaks that number line up into two pieces, right? We're just going to test on either side of 2 to see whether the acceleration is positive or negative. So I can just choose a value on this side, say 0. I can plug it into my acceleration, which is 6t minus 12. Plug in 0, you get negative 12. So on this side, my acceleration is negative. Likewise, choose a value over here, any value, say 3. Plug it into your acceleration. 6 times 3 minus 12 is 6, which is positive. So my acceleration over here is positive. So I want to compare this to my velocity. So I'm just going to recreate that velocity diagram we made. And that was broken up at times 1 and 3. And that's where my velocity was 0, and it went positive, negative, positive. All right, so the particle will speed up when the signs agree with each other. It will slow down when the signs disagree with each other, right? So let's look. We're going to start at time 0 for both of these. Well, from time 0 to time 1, acceleration is negative, velocity is positive. So that means they disagree and it's slowing down. So it's slowing down from 0 to 1. All right, but then from 1 to 2, our velocity has changed. It's become negative. So we're negative velocity and still negative acceleration. So time 1 to 2, they agree, so it's speeding up. All right, let's look again. 2 to 3, we're still negative velocity here, but we're positive acceleration. So 2 to 3, they disagree, it's slowing down. All right, and then finally from 3 to infinity, we're positive acceleration and we're positive velocity, so it's speeding up from 3 to infinity. Which makes sense, right? Because remember when we went over the distance it traveled over that last trip, the last time it turned around, from 3 seconds to 5 seconds, it traveled 20 meters, which was way more than the first 2 trips. So we kind of posited, oh, it must be speeding up there. And it is. All right, that's it. We've dissected everything we could about that particle. That's the particle dance. That was going to be my teacher talent show thing this year, is to go up on stage and just like start a timer for 5 seconds and do this. And only the CAC students would get it, but I'd be imitating the motion of this particle. All right. there's that sketch that I was talking about that we skipped in part E, but you probably have seen these motion diagrams in Steiner's class. You won't have to do that for me. All right, so the other idea, the big idea from kind of 4.1 is just interpreting a derivative as a rate of change, right? And so that's we've been doing that using physics already. So the rate that position changes is called velocity. The rate that velocity changes is called acceleration. The rate that acceleration changes is called the jerk. But you can also apply it to any other science. And the way I would want you to do that, the way I always think of it is whatever the units are that they give you, think of those on the x, y axis. So like the rate at which water flows into or out of a reservoir, you may be given the time on the x-axis, and then you may be given the volume in gallons on the y-axis. Then think of, okay, what would the slope of that graph be in units of? So the slope would be rise over run, which would be gallons per whatever unit of time, per second. And that's a flow rate of water, right? That's the rate of change of volume of water in the reservoir, which would be a flow rate of water. And you can do that with anything. So urban geographer is interested in the rate of change of population density in a city as the distance from the city center increases. Meteorologist is concerned with the rate of change of atmospheric pressure with respect to height. So all of those are rates of change. A rate of change is a derivative in calculus. Yeah, and this just kind of reiterates that the abstract ideas of derivative, when you apply it to contextual scenarios, we think of it go from slope to derivative to rate of change, and the way to figure out what the units of that rate of change would just be to put the y units over the x units of whatever it is you're talking about, and that's it.